Hello, everyone. My name is Yuvraj Singh. I am a senior biochemistry student. I'm currently working with Dr. Lin Zhao in his Department of Chemistry laboratory. My study focuses on the impact of DNA binding on the enzymatic ability of alkyladenine DNA glycosylase. So the mitochondria is an essential organelle for every cell. It's responsible for ATP generation, metabolism, oxidative stress control, and can also be involved with cell death through apoptosis. What's interesting about the mitochondria is that it also contains within it its own mitochondrial DNA. And the mitochondrial DNA is responsible the for coding for the proteins for the TCA, the electron transport chain, and the maintenance of its own genome as well. And it's very important that this genome stays integrally sound. Otherwise, it can lead to a lot of mutations, the compromise of the mitochondria and the compromise of the cell itself. And of course, like as I mentioned before, it can also lead to apoptosis. So, as I mentioned, DNA damage is very important to control, and this DNA damage can occur through a variety of forms. We have reactive oxygen species, strand crosslinks, radiation, bulky bases. So there's just a lot of things that can damage DNA, and DNA is obviously very easily damaged. This is not just mtDNA, mitochondrial DNA, but this is also common in nuclear genomes as well. And so the mitochondria and the nuclear genome have come up with mechanisms that will go in and repair these damages that have been done. And so one of them is called the base excision repair pathway. And so this base excision repair pathway focuses on damages that occur through alkylation, deamination, and oxidation. And so if you look at the right, this mechanism here shows how DNA damage is repaired through base excision repair pathways. So if you look here, DNA damage occurs. So let's imagine that this X indicates the damaged base. And then a protein called DNA glycosylase will come in. And this glycosylase, what it does is it goes through a very processive method of looking at for a very specific type of damage. And it'll go ahead and recognize this damaged base, and it'll excise this damaged base. So it'll remove the base from the DNA, and it generates an A basic site. So this A basic site is basically, this will begin the overall pathway for the base excision repair pathway. And so DNA glycosylase allows for AP endonuclease, GRP lipase, DNA polymerase, and ligase all to come in and basically bring back DNA to its original form and repair the damage done. So, as I mentioned before, glycosylases are very important. And one of the proteins that I'm studying is called alkyladenine DNA glycosylase. And this protein localizes in both nuclear and mitochondrial DNA regions. AAG, in short, is responsible for removing damaged bases, as I mentioned before, and it initiates the overall base excision repair pathway. The other protein that I'm studying is called mitochondrial transcription factor A, or TFAM. Now, this protein is a binding protein that also localizes in the mitochondrial DNA region. And this protein is specific only to the mitochondria. It plays integral roles in packaging stability, replication of the mitochondrial genome, and it also has its roles in cell repair and inflammation responses. And so with both of these proteins being localized around the same area, it's likely that they also interact with each other. So that is where my study focuses on. What we want to do is we want to study these two proteins and see how the TFAM, transcriptional factor A for mitochondria, and AAG interact with each other. So does the presence of TFAM cause stimulation, inhibition, or does it just not do anything? Or is it the other way around, where AAG will come in and inhibit TFAM binding to the double-stranded DNA? So for this study, I'm focusing specifically on the ability of TFAM to either stimulate or inhibit the catalytic activity of AAG. So the methodology that I went through was called, I went through an assay called a TFAM stimulation assay. So this assay is a kinetic assay that focuses on basically competing these two enzymes against each other and seeing if the binding of one enzyme impacts the ability of the other enzyme to bind and perform its duties. So what happens is, so in this assay, what I did was we use a double-stranded DNA, and this double-stranded DNA has a base, a hypoxanthine or inosine base. So this is substitute for the damaged base that would be found in the mitochondrial DNA in an actual cell. So we use double-stranded DNA with hypoxanthine and inosine, and what we do is we add TFAM to this hypoxanthine DNA, and we do this through different concentrations of TFAM. So we dilute TFAM into multiple different concentrations, and we also dilute AAG to multiple different concentrations. So for this assay, we diluted it to 200 nanomoles and 400 nanomoles. And I wanted to study the different catalytic activity of 200 and 400 nanomoles. We first add TFAM to the double-stranded DNA to ensure that TFAM is able to bind. And then we introduce AAG to see if TFAM binding to the double-stranded DNA will impact AAG's glycolytic activity or not. And this assay follows a certain timetable. So we add TFAM to DNA for about 4 minutes, then continue and add AAG. So this, of course, this assay's timetable is it's variable to change. So it can change depending on how many points I'm studying. But it's done at 37 degrees Celsius, which is the optimum temperature for binding to occur. And we visualize all of this with a 16% SDS urea PHO. So these are some preliminary results. At first, we wanted to see what exactly happens when AAG is introduced to TFAM. So if you look at this gel on the left, we look at the left side of the gel. This is the 200 nanomolar data. So we can see that with AAG only, so this is our control, it only has the alkyladenine DNA glycosylase. There's a certain product form, but at 0.2 and 0.5 micromolar concentration of TFAM, we can also see that there's a significant amount of product form. And at 1 and 2, there's a significant drop in the amount of product that is formed. When we look at the data below in the data table, it's clear to see that the control is 5.84, but the concentrations, the low concentrations of TFAM actually stimulate some product formation, so stimulate some glycolytic activity for AAG. And this is even more evident when we look at the 400 nanomolar concentrations. And this is, it makes sense, right? Because there's more AAG, so that means there'll be likely more product being formed. So when we look at the AAG for 400 nanomolars, we can see also that there is a clear increase in the amount of product being formed. When we look at this graph here, it's very clear to see that there's a little bit of stimulation seen around 0.2 and 0.5 micromolars of TFAM. And after that, it drops down into almost an inhibiting state after around 1.0. And we can tell it's inhibiting because it's actually less product formed than just the control, which is just the AAG alone. And so the next step we wanted to see was whether or not this data was consistent throughout the lower points. And so this experiment was repeated with more points in the 0 to 0.5 region. And what we saw was similar to the last results, right? Because there's a stimulation. If we look at image C here, there's a stimulation we've seen around 0.1 through 0.5. And then afterwards, we see a significant drop in the glycolytic activity of AAG. And when we look at the tables, that's also very clear. If you look at the 400 nanomolar table, you can see that the 0.1 through 0.5 is significantly higher than the controls and the 1.0 and 1.2 region, 1.2 micromolar concentrations. So it's very convincing that there is stimulation going on at these lower concentrations of TFAM. And what we wanted to do next was add even more points. So as you can, if you remember from the last slide, there's about 6 points here, and they're mostly focused around the earlier concentrations, the lower concentrations. But we wanted to see if there was a gradual drop in the overall stimulation or glycolytic activity, or was there another peak, or whether or not it was inhibited at all. What we saw was that if you look at this gel, there's obviously very significant stimulation and glycolytic activity at these earlier concentrations. But when we look at these higher concentrations, there's a significant gradual drop of stimulation and glycolytic activity. If you look at this data, you see 19.56 all the way up to 28.41% product. So it's TFAM here is very much stimulating the glycolytic activity of the DNA glycosylase. It's very evident when we look at this graph here as well. We see a significant increase from the blank, and we see that there's stimulation occurring from a 0.1 all the way up until 0.5 micromolars. And so this is very consistent with the other data we found as well. And then when we look at the higher concentrations, we see that there's a gradual decrease in the amount of product being formed. So that means that at higher concentrations, it's likely that TFAM outcompetes AAG for binding, and it does not allow for the substrate to bind to AAG and AAG to perform its glycolytic activity. And so this makes a very convincing argument that in certain conditions, TFAM and AAG are able to stimulate growth, and at some points they're able to inhibit growth. So the takeaways here are that TFAM at lower concentration is able to stimulate the glycosylase activity of alkyl adenine DNA glycosylase, AAG. And that at TFAM at higher concentrations, after about 0.5 micromolars, it causes a gradual decrease of AAG glycosylase activity, and it inhibits activity at very high concentrations. So the future steps, as this is an emerging concept, the future steps is to study if this effect it's consistent with different lengths of DNA. So right now I'm using 19 MER for the length, but I want to study if there's different results when we change the length of the substrate itself. So there's more opportunity for binding and more opportunity for glycolytic activity. So there's also research that shows that AAG is very sensitive to salt concentration. So what I also want to do is able to manipulate the salt concentration, so NaCl concentration, and see if it changes the result, because AAG binding is it's very sensitive to NaCl concentrations. And so we want to see if this changes any results with the glycosylase activity of TFAM, of AAG while TFAM is present. As for acknowledgements, I want to thank you for letting me present for the Undergraduate Research Symposium. I want to thank the student engagement for the opportunity to present. And of course, I want to thank my PI, Dr. Lin Zhao, for the constant support and guidance throughout my training. And of course, Kathleen for my in-lab training and support, helping me understand the complexities of research with enzymology and just teaching me basic general laboratory etiquette. Thank you so much. And any questions?